Hello, everyone. Hakan Ohlgren, St. Jude Medical. I've been in this business for 2.5 years, approximately. Earlier, before that, I came from the telecommunication business. And talking about body-air network, I can't really not comparing to the technology of mobile phones or cellular phones or, the Bluetooth network. It's really very similar to what we're trying to achieve with body-air network. In the mobile phone business, just before I start this presentation, I think we have a regulatory, much more simpler situation, of course. So we couldn't really compare everything, but we should also understand that there are standards out there that is already accepted. Bluetooth, Wi-Fi, Zigbee, all those standards are available, and we shouldn't try to redo all these very heavy and very expensive work to push for a new standard. So keeping this in mind, I think is important when we go through the presentation. So I will cover where we are today, from St. Jude being a company that works with several different companies, different medical implants. I come from the CRM, the Cardiac Rhythm Management division. So I will talk about that. We also talk about the future of, and being more emphasizing the future of telemetry. I will also have this why body-air network, and I think that would be for more discussion of this workshop. Just a very, very short summary of our company, and what I would like to highlight here is that when we talk about body-air network, we are doing a lot of different products within our company. We're doing products for atrial fibrillation, cardiovascular, neuromodulation, and cardiac rhythm management. Many of these products, being medical implants, are actually realistic to be included in a body-air network. So for us, this is important to understand what we're going, what we can do, and of course, understanding the risks. Very close or very similar to Medtronic's system view, we have different equipment out there that is in use for several years back. Before RF was used for telemetry, for the communication between the medical implant and the whatever, let's refer to it as a base station outside. It's a base station. In the clinics, we use this programmer, and we still use the legacy inductive one telemetry. So before RF, we use inductive. Today, we actually start up the devices, the communication with inductive, and then we go over to RF communication. And we shouldn't forget about the many physicians actually doesn't really rely on RF yet, even though the technology have been there for several years. There's still a reluctance of using RF sometimes, because RF in its nature is very unstable to people's mind. You can have people understand the in-clinic situation. You're doing an implantation of the device. You're actually using the X-ray machines quite often. When you implant the leads into your heart, you use the X-ray machine, meaning that the physician and the rest of the people in the room, they are using lead aprons. And having those lead apron people moving around in the room, they will for sure sometimes hinder the RF, or at least they will change the RF fading in the room, so that the communication might break. And in this situation, if, for example, the ICD is an implanted device, if you're implanting a device that actually should shock the heart, what you do to set the levels, the energy levels that are required to make your heart running in the normal pace again, you start the heart in a fibrillation. You actually trigger the heart to run faster than it should. Let's assume that you do that and then your RF link breaks. That is not good. So you need to rely on the link so that you can start it, then reset the heart, try and set the correct level of energy that is required. And if the physicians can't rely on RF, then we wouldn't use it. Now, this is one example, and as time goes along, and actually, of course, the use of RF and the trust in RF is getting better and better. Now, We are also using the mixed band. I don't have to dwell on the technology here. One of the parameters would be the data rates. We are using different data rates, and the thing with this med radio, or specifically the mixed band, the core of med radio, is that it's standardized in the sense of channel bandwidth and number of channels and the frequency band. The protocol is not standardized. We have a proprietary protocol used for St. Jude Medical. There's another proprietary protocol used by Medtronic. And all the competitors using this mixed bands or med radio will use proprietary protocols. So by that, we can't have a standard with a device that is kind of a common device for every medical implants in the world, being supported by one device made by some manufacturer. We use, during the follow-up, the same programmer system. So if you go to a hospital, not only in the implantation center you use this equipment, but also in the follow-up room. This room is not as critical. There is now people with lead aprons running around. There's a smaller room. You for sure have RF fading, so the channel, the radio channel that you use is still a noisy channel, and it can be subject to disturbances that actually make the channel to break. But it's not a life-critical scenario. If you can't read out the data, you'll try again. Now, going to the remote monitoring, this is, I guess, more interesting from a body-area network point of view. When the patient is at home and he had this bedside monitor, we can schedule the pull out of data from the implant, or you can use that manually. As being the patient, you can, when something happens, you feel odd, you feel strange, something happened, I can push a button and the device will read, or the remote monitor would read out my implant data and send that to the network. We have this called Merlin.net, which is a database storing all the patient's data, with the idea that the physicians can go into that database and read out what trends, what happened the last 24 hours, what happened in the last months or whatever. So, as I mentioned, we can schedule this. We have a problem with all the medical devices that is implanted, that is related to longevity. You mentioned the lifetime of the battery, and that is for sure one of the most critical things that we need to keep in mind when we talk about body-area network. Even if we could, and even if we would like to schedule that we take data from the implant to the Merlin.net very often, several times a day, we would for sure not be able to take all that data and do something with it. That's one thing. But it's very much related to each and every patient. So one patient might need more regular measurements, while another patient might need once a week only measurements. But the battery in the device would for sure drain if you read out very often. And the amount of data is increasing. You could argue for, okay, so if you would like to make, to only take the data, what happened the last 24 hours, did you have any shock delivered? Did you have some kind of threshold of the heart rate passed, under or over limit? That data is very little, but if you read out more data, if the device is starting to trend things based on temperature, pressure, heart rates, what have you, then it becomes more data, and then each and every reading would consume battery and shorten the longevity of the device. If we have to then extract that data more often, of course, then we have even shorter longevity. Okay, so going for where we see, and taking a little bit of what I've now said into account when we talk about body-area network, we have the implant that is very sensitive to power drain. Okay, so we can't use much power for the RF. The RF is just a tool to get the data out of the device. One of the options with body-area network would, of course, be that our implant is the hub, the central hub of a body-area network. in not only on body-worn sensor, but also implanted sensors like blood pressure sensors, temperature sensors, what have you. They could communicate with our implant. The problem is that the body attenuation is extremely high. And the energy that is required to do this communication is, of course, a problem then. Not only talking about charging batteries, because you can, in theory, recharge batteries. You can have sensors that are charged during the night when the patient is lying in a bed. You can have some chargers under the pillow or under the bed. But you can't rely on that, especially not for life-treating devices like the pacemakers or defibrillators. So this picture really takes that into consideration and says that, okay, so the hub is an external device, and that communicates with the medical implant in the most power efficient way, using MedSped or MedRadio band. Then making use of all the other standards that were already mentioned, Bluetooth, Zigbee, Wi-Fi, whatever is available today can be used by the other sensors, the body-worn sensors. So this would then have to be a multi-RF device, a multi-channel device, multi-technology device. Still, the link to the medical implant is a proprietary protocol. So this device cannot be just whomever that delivers that. It has to be a device that either you have a soft radio where St. Jude Medical or Medtronic or Boston or whomever actually stands behind the protocol, the software, the firmware that controls the radio so that it works with our implant. Or we have to develop and deliver that product. So this could be a St. Jude device or a Boston device or a Medtronic device. That makes things a little bit more complicated because I think that there is a huge market out there that would like to develop these hubs. And for sure, if this would be, for example, I mentioned the ANT Plus, which is it's an accelerating technology used right now for sensors, body-worn sensors used for training, runners, biking or cycling. This is a very interesting technology used. They have the pulse meter only, I think, today. So they have the watch or a GPS transmitter or whatever, or a receiver, or that will present the speed, the cadence of your biking, the pulse, the temperature, and everything that would be of interest. This is exploding right now. We have cellular phone manufacturers that are supporting ANT Plus in their cellular phones, just to be able to support this enormous market of training supporters. There would be multiple of applications downloadable both for iPhones and Android phones that supports this. But also they support Bluetooth, of course. So Bluetooth standardized, protocol standardized also, sensors would be supported by all these phones. Would this device be a generic mobile phone using iPhone or iOS or Android? That's what we need to figure out. Everyone that is working with body air network, can this really happen if we use a device that is generic? Should we use a St. Jude medical application and then download that into this phone to make it this proprietary link work as expected? Would that be okay by legal, by the ethics, all these regulatory requirements that we have? Would that be even possible to get through? This is part of what we have to study. Also, we need to be very careful when we talk about new standards. The longevity, I talked about the longevity of the implants. Today we have something like 7 to 10 years longevity in our devices. We shouldn't forget about the people that are getting an implant today. They would like to have support 10 years from now. And they need to have the same technology support that we develop in the future. So if we have a body air network that really delivers higher quality of life for the patient, we need to give that to the patient receiving the implant today as well. So legacy support is important. Once again, that would emphasize that this might be a St. Jude medical device or a Boston or a Medtronic device, not whatever device. I mentioned the different problems that we have when we have a medical device implanted into the body, and one of them is the attenuation through the human tissues, muscles, fat, the skin. We have issues always when we implant something, and the physicians are placing the devices at different depths. It's both physician to physician, but it's also market to market. Some markets tend to have them submuscular devices, and some have even more deeper submuscular implants. You could argue for whether you should place it just under the fat. That is not that common, but when we talk about different devices like neurostimulators or neuromodulators, they might not be implemented in the same area where we have a lot of muscles. They might actually be implemented in a place where you have more fat only. So the human attenuation, the human tissue attenuation is a problem. That comes with the frequency of the telemetry link then. If we have higher frequencies, 2.45 gigahertz, for example, is very much worse than using 400 megahertz, which is the med radio band. So we would also see variations, as I mentioned, 5 to 6 dB, and 6 dB correlates to double or half of the operating range. So it's not small variations we're talking about. If we have one device implanted into this guy and you receive another device, it might be that I can communicate with you, but you have to be in the half of this operating range before I can reach the communication. Next thing, of course, is the path loss, which is it's a natural law. We can't do anything about this. The RF signals are attenuated through the air, and that attenuation differs between the two frequencies, or the 245 and 400. Of course, it's dependent on the frequency itself. But in this example, 245 and 400 megahertz differs actually 15 to 16 dB. And going back to the root of everything, battery longevity again, higher frequency requires more output power because of the attenuation in the body tissue and the free space loss. And higher output power means more power from the battery, means lower longevity. So you see everything, when we talk about medical implants, we are very afraid that the medical device will not act in the same way as we're used to. Longevity is really core essence for the patient. Why body air network then? What we see now is the healthcare cost is is rapidly increasing, and it's extremely expensive today. And what we see is that they will be enormously expensive in the future. We need to reduce the time that the patient is using of the hospital's resources. Then again, we have the trade-off. When the physician, he will not be the guy just sending an SMS, everything is okay. He wants to meet the patient. And the patient often, if you're an old person, you would like to have this very close. We shouldn't forget about the psychological parameter. This might be actually one of the few people that you ever meet. And when you talk about your health, this is extremely important for him. I saw one of your slides was showing a video conference scenario where the doctor meets the patient over video. That might be a solution. It might be a possibility. Still, that is using some resources. The physician will still be there in the other side. That will consume time. So we have higher requirements by the patients as well. Now, technology is reaching, you can see iPhones or iPads in people of quite old people. And that's not so strange anymore. People are used to new technology. People are accepting new technology as they go along. Applications for smartphone is very well understood and very well accepted. So we shouldn't say that, well, this is a young people thing or this is an old people thing. That's not true anymore. Lifestyle related issues. You're traveling. So if you have a device that is accepted on a certain market. My device talks with a frequency and an output power that is accepted in Europe. What if I go to US and travel to US and I get sick there? I go to a hospital, I have a St. Jude medical implant, I go to the hospital that are supporting St. Jude medical implants. but they are not supporting the same output power or the same frequency. That would be an issue. And we for sure have to support a worldwide scenario based on the fact that people are traveling, that they're changing the lifestyle. This is where it becomes sensitive. We can make use of multiple sensors in a totally new way. And when we talk about, this slide, I changed this slide because it said from start, high quality, reliable, automatic, well, I don't recall what I said. What I meant was actually I can get really a clear view of what kind of disease I have, or are you getting worse? Are you getting better? What should you do? Should you change your medication? Now, that would be very sensitive because the physicians, of course, would like to be physicians. They would take control over your health. They would be your aid. If we have a device that automatically says something, if this would be a mobile phone, let's say that you download an application that includes a virus that changes your indications to you, saying that everything is good, but you have a severe health disease and a health disorder right now, you should actually go to your physician, but you get a green light. That is not acceptable. So, summarizing where we are, we need to use the sensors to improve the trend analysis, but the sensitive part is how far can we go in reducing the time the patient meets the physicians and make use of the resources of the hospital. Last slide would be standards. I mentioned this in different slides. There are multiple standards out there. We have the Nth class, we have the Bluetooth, Zigbee, all the proposed standards for body-arm networking. There are multiple companies out there that would like to supply sensors. There are already sensors with the weight scale sensors, you have the blood pressure sensors and stuff. If we have a standardized system, can we really choose what devices are allowed in the body-arm network? Let's say that you buy a very cheap consumer electronics device, an extremely cheap device. The accuracy of that one is not nearly as good as the high medical graded device maybe. So how can we stop or limit the use of sensors? Only using good ones, not bad ones? Who should define what is good or bad? That is part of the standardization to cover. Thank you very much.